Welcome to another tutorial which will take us deeper into our deep learning journey. Previously, you learned how to use the Bellman equation to predict accurate expected values for state action pairs. The value of a state is equal to the Q value for the best action. There are two distinct tasks in reinforcement learning. One, calculating accurate expected returns, value. Two, deciding which action to take, policy. Our previous efforts in QLearning focused on making accurate value calculations, and finding the policy was as simple as doing an argmax over the Q's of every possible action. But to get state-of-the-art results on the tough reinforcement learning problems, we're going to need to change our approach. Deep QLearning doesn't work with large or continuous action spaces. Policy methods do. Policy gradient methods deal directly with tweaking the policy function without the need to compute precise values. A policy network returns a matrix of probabilities for taking each possible action. We can either greedily take the action with the highest probability, or, especially during training where exploitation is important, we can take a random action based on the weighted probabilities returned. Policy is usually represented in mathematical notation with the symbol pi. Policy gradients can be summed up like this. 1. Start out with an arbitrary random policy. 2. Sample some actions in the environment. 3. If the rewards are better than expected, we increase the probability of taking those actions. 4. If the rewards are worse, we decrease the probability of taking those actions. It's as simple as that. The policy network outputs raw numbers called logits, which are input into a softmax function. The softmax function squeezes the number into probabilities between 1 and 0, which all add up to 1. These probabilities are used to select an action. Let's take a look at the policy gradient loss function. Loss equals the negative Q of S and A times the log of the policy for the action and state. The minus sign is important since we minimize the loss function during stochastic gradient descent, but we want to maximize the policy gradient. So why use log probability instead of just probability? Probabilities between 0 and 1, when multiplied repeatedly, can get very close to 0, which results in a float underflow error where it can essentially just become 0 and screw up our training. Logarithms, on the other hand, are more numerically stable and perform better. Backpropagation math is also simpler and faster in the logarithmic space. Let's take a look at one of the simplest policy gradient algorithms called reinforce. This is as simple as it gets, and later we'll learn some tweaks which improve results but complicate things slightly. Step 1, initialize the network with random weights. 2, play n full episodes, saving their S, A, R, S prime transitions. 3, for every step t of episode k, calculate the returns for subsequent steps. This is the same Bellman equation, but we were dealing with multiple complete episodes, and that's the only difference. 4. Calculate the loss function for all transitions. Multiply each calculated Q value for each state and action taken by the log probability from the policy for that state and action. Sum them up and then subtract them. Step 5. Perform stochastic gradient descent. Update the weights and minimize the loss. Step 6. Repeat from step 2 until converged. Alright, now let's take a look at the main differences between vanilla QLearning and policy gradient. First, no explicit exploration is needed. Instead, the network returns a probability distribution for the actions, and we use that to choose random weighted actions. In the beginning, probabilities are very uniform, which corresponds to random behavior. Later, as the agent gains more certainty in correct actions, the actions become more deterministic. Policy gradient methods are on policy, which means we must take our training data from episodes played with current policy. Using data from old policies will screw up our training. Policy gradient usually converges faster than QLearning, but it often requires us to play more episodes. We still need a large buffer of transition data to train on to avoid high correlation between samples, so we solve this by playing multiple episodes using the same policy between each update. Finally, no target network is needed. We use Q values calculated from experience in the environment rather than estimations from a neural network. This saves on memory and makes training faster. Alright, now let's see how we can take the generic reinforced algorithm and kick it up a notch. The first thing we're going to look at are multi-step Bellman rollouts. If you recall, temporal difference learning traditionally uses two states, the current and the next. Training the network on longer rollouts can improve performance. To calculate returns in practice, we loop backward through the rewards from last to first, multiplying gamma at each step except for the first. Basic Bellman equation again. The total discounted reward and the last state is returned. The last state and the rollout substitutes for S prime during training. Too many steps will decrease performance, so this is a hyperparameter that needs to be tuned. And in the real world, the variance of the rewards can be very high and outliers can screw up our training. Instead of scaling the policy gradient based on gross rewards, let's scale based on whether they are better or worse than expected. To do this, we subtract the average expected reward baseline from Q. The simplest way is to keep a moving average of returns and use it as the baseline. We can also use the value of the state, but this is a little more complex and we'll implement it in the actor-critic architecture. The next trick we're going to take a look at is the entropy bonus. Policy networks can easily get stuck in a local optimum and the agent stops exploring, so the policy ceases to change. Entropy is a measure of the uncertainty in a probability distribution. And recall that entropy is the sum of all the probabilities times each log probability. By adding an entropy bonus to our loss function, we can punish the policy network for being too certain and encourage further exploration. The policy gradient algorithm by itself is rarely used because it has been replaced by more effective algorithms such as actor-critic and PPO. But in order to understand how these algorithms work, it's important that you understand vanilla policy gradient, which is the method we're going to be building upon. I'm going to keep this coding tutorial very simple with the intention that you understand how the code works. In order to keep it simple and allow fast training, we're going to work with the classic cart pull environment. The goal is to move a cart back and forth to prevent a balanced pull from falling over. Actions are left and right. We get 1 point for each time step that the pull doesn't fall over, and 200 is a perfect score. We're shooting for an average score of 195 over 100 episodes. This tutorial uses a reinforcement learning helper library called PTAN. This stands for PyTorch Agent Network, and you can find it on GitHub. This contains some helper functions for interacting with GIM environments, calculating returns with the Bellman equation, and action sampling strategies like softmax, which we're going to use today. All right, let's dive into the code. The PGN class is our neural network. For this demo, we're going to use a very simple multi-layer perceptron with inputs, outputs, and a single hidden layer of 128 units. Mean buffer keeps a moving average of rewards. We're going to scale our gradients based on the average reward over the last 50,000 or so time steps. If the reward is better than average, we increase the probability of taking the action. If it's worse than average, our loss function will decrease the probability. Moving on to the hyperparameters. Target reward is the mean reward over the last 100 episodes, which we'll stop training if we reach. Gamma and learning rate you should be familiar with by now. Batch size is the number of randomly selected transitions we process each step of gradient descent. Entropy beta is the relative strength of the entropy bonus subtracted from the reward function. The higher this value is, the more the agent will be incentivized to explore. Bellman steps. How many steps of rewards are factored into the total reward for each SAR S prime transition? And baseline steps. The length of the moving average for calculating the baseline. Moving into the main loop, the first thing we're not familiar with is the policy agent class. This is responsible for inputting the state into the network to get back logits. It then applies a softmax function to get probabilities and samples in action based on the calculated probability distribution. The experience source first last class interacts with the environment over the given number of steps, discounts the rewards with gamma, and returns a single SAR S prime transition with the first state and the last state encountered. And as before, we're going to use the atom optimizer. Now we'll use the experience source as an iterator which returns a single transition each loop. We add the latest reward to the baseline buffer. We calculate the mean baseline from the buffer. We save the states, actions, and scales, reward minus baseline. Interestingly, for policy gradient, we don't care about state prime since we aren't calculating the values of states. If the episode is over, we do some statistics tracking and check if we've reached our target reward. Now we copy the data needed for training into PyTorch tensors and send it to the GPU. And as before, apply a stochastic gradient descent with the atom optimizer. The net returns logits, which are arbitrary numbers which the softmax function squishes into probabilities between 0 and 1, all adding up to 1. To avoid losing math precision, there is a function which will apply the softmax and return the log probabilities in one shot. We now multiply the log probabilities of each action taken by the reward minus baseline scale. We take an average of the action log probabilities across all batches. Then we flip it negative since we're really applying gradient ascent and want to increase action probabilities for higher than average rewards. Next step is the entropy bonus. We want to encourage exploration by rewarding it when it is uncertain about which action to take and thus likely to act randomly. We take a softmax to get raw probabilities for each action. Entropy is calculated by negative raw probabilities times log probabilities. This is then scaled by the entropy beta and subtracted from the loss function as we want to reward positive entropy. Finally, we backpropagate the loss and update the weights with the atom optimizer. The rest of the code is simply to graph useful statistics about the training process. These can be useful to debug your hyperparameters and algorithms when training isn't going as expected. The first thing we'll calculate is KL divergence. This is a measure of how an actual probability distribution differs from an expected probability distribution. In this case, we're going to compare the probabilities returned before and after the gradient update. High spikes are a bad sign as drastic changes in the policy gradient can screw up training and be hard to recover from. Cutting-edge reinforcement learning algorithms like PPO focus on keeping changes in the policy gradient gradual throughout training so that outlier data doesn't derail the whole process. KL divergence is calculated simply by cross-entropy minus entropy. Next, we graph the baseline, entropy, batch scales, entropy loss, policy loss, total loss, normalized gradients, and the maximum of the gradients. Then, we just continue looping one step at a time until we reach the target reward. I was able to solve this on average in around 75,000 frames. Perhaps you can tune the hyperparameters and make it better. Let's take a look at the graphs. The rewards look good. Our algorithm is definitely learning and definitely mastering the game. The baseline is converging exactly as we expect. This is the average reward over a 10-step period, and the environment gives us a reward of 1 per step. So with the discount factor of 0.99, we can expect this to converge around 9.5, which is exactly what it's doing. The batch scales are decreasing over time, which means that the actual rewards are getting closer and closer to the expected rewards. Entropy is decreasing over time, which shows that the policy is getting more and more certain over which action is correct. Here we compare the individual components in our loss function. Entropy loss is increasing over time due to our agent becoming more and more certain about the actions. This is a flipped mirror of the entropy graph you just saw. Our policy loss is decreasing over time, which shows the network is converging, and the total loss function looks much like the policy loss. We want to check that the entropy loss isn't dominating too much. On the gradient graphs, we just want to make sure we don't have huge spikes. This looks fairly normal. And on KL divergence, everything is good if our spikes stay mostly below 1e minus 3. Alright, and now you have a solid primer on how policy gradients work. If you feel confused, make sure you go back to the math prerequisites section and make sure you fully understand logarithms, entropy, cross-entropy, KL divergence, and the softmax function. I was seriously having trouble understanding what was going on, and that is what made it all click for me. So next time, you are going to take the next step toward the latest cutting-edge reinforcement learning algorithms, which are able to take on much more difficult challenges than what we have learned so far. What happens when we combine deep QLearning with policy gradients and allow two dueling networks to improve each other. It's called actor-critic, and you'll find out how next time. This is Colin Scow. I'll be back soon, and until then, happy coding.